I'll be talking about hybrid machine learning methods for the interpretation and integration of heterogeneous multimodal data. Now, I've been doing research in the field of machine learning for about a decade now, since I started my PhD. And over this time, we've all seen, I'm sure, a sharp increase in data abundance and computational capabilities. And this has, of course, opened new possibilities for the training of machine learning models, both in terms of their variety and the scale of the models. In the area of health specifically, where I get most of my data, electronic health records are now widely collected, and increasingly they're made public. Now, smartphones and wearables have, in the meantime, become ubiquitous, and this, of course, led to a democratization of data collection. So we've now seen a surge in multimodal data that's noisy and non-uniform. The data sets are collected across multiple populations and multiple institutions at an unprecedented scale. Now, over the years, we've all seen powerful specialized techniques that have been designed to handle distinct data types, such as images, time series, and video. However, we've seen comparatively less effort allocated to approaches that can handle these multimodal heterogeneous data that are collected in a non-uniform manner. And we'd like to find ways to integrate these many different types of data, as well as make them more accessible to human users. In this context, my aim is to build hybrid systems that integrate multimodal, multi-source data and learn models that aid users interpret the data. There are three aspects to my research. First, the interpretability component. Second, the hybrid systems. And finally, the integration component. During my PhD, I've studied methods for partitioning data and leveraging low-dimensional structure to enable visualizations and annotations by humans. I've also worked on constructing hybrid models that combine deep learning with random forests, and I'll talk about that as well. And during my postdoc, my research centered more around the integration of structured information into temporal representation learning. Most recently, I worked on an application that combines all three aspects to achieve large-scale, weekly supervised classification of cardiac MRIs. Toward the end of my talk, I'll outline some directions for future research. The first project I'll go over addresses the interpretability aspect, the interpretability requirement. So let's start by considering a vital sign monitoring system which issues healthcare alerts whenever one of the patient's vital signs is out of its normal range. So as it happens, the alerts are quite frequent. In a typical step-down unit, we have one alert go off every 90 seconds. So every minute and a half, the patients and the caretakers are interrupted by these alerts. Luckily, some of them are false alerts. They're called artifacts, and they're due to the limitations of the monitoring equipment. The objective is, of course, to adjudicate the true alerts and distinguish them from the artifactual alerts. We worked with multivariate vital signs that were collected non-invasively. These are heart rate, respiratory rate, systolic and diastolic blood pressure, as well as oxygen saturation. We extracted features from each signal, computing statistics for the duration of the alert window and a window of 4 minutes preceding the alert. In this case, it's not just enough to build a classifier. We need a model the doctors can trust so it can be validated. So we need interpretability. Let's discuss interpretability for a minute. Assume that we have these two views of the data. So in both cases, the true alerts are shown in red and the artifacts are shown in blue. If we plot respiratory rate versus respiratory rate increase, which is what's shown on the left, we're going to see that there's no separation between the true alerts and artifacts, so this view of the data is not very useful. On the other hand, if we plot oxygen saturation density versus heart rate density, we can see that the artifacts are obviously separated from the actual alerts. So if we get an additional sample that's marked by the X in the plot, we can easily classify it as a real alert. It's, of course, located in an area where there are a lot of real alerts, so it's easy to see why it's an alert, not just that it is an alert. Of course, there's been a lot of work on feature selection, but this method goes beyond that. And let me just explain how it goes beyond that. So we could just take the two most informative features and provide 2D plots. And we can see here the respiratory rate density versus the blood pressure density, which are the two cleanest features in this data set. And we can see that most of this data in the plot is nicely separated, but there's a portion that contains noisy samples in that top right corner over there. Now, this happens with data no matter how good the features are. There's going to be some portion of the data that's difficult to classify. What our method does is it takes these samples and handles them with a different low-dimensional view. So it finds specific low-dimensional views that handle difficult samples, difficult cases. Let's look at this artificial case. There are obviously two groups of samples, and we can see them. The group on the top can be classified with the y-axis, and the group on the bottom can be classified with the x-axis. Our method partitions this data and projects each group on its relevant features and then trains a classifier on it. In general, in a higher dimensional space, we split the data into several subgroups based on the existence of low-dimensional structure. Once we project the data on their specific informative projections, then we can train low-dimensional classifiers on those informative projections without having to look at the whole data set. Now let's go back to our application, and let's assume that we have this table where each row is an alert and each column represents the extracted feature. Again, each alert can be a true alert or an artifact, and we're trying to build a classifier. Our machine learning tool, called VIPR, partitions the data and extracts projections in which the alerts are either convincingly real or easily dismissible as artifacts. This is one of the two projections we obtained when classifying respiratory rate alerts. So we can immediately see that the true alerts are distinguishable from artifacts. They're very cleanly separated in that plot. We've also tested this model in terms of accuracy against random forests and support vector machines, and it outperforms both of those methods. This is the second projection obtained by the model. So just remember that our model obtains multiple views of the data, and it partitions the initial data set. Now we can see that the artifacts are clustered in the lower left side of the graph when density values just get very near zero. Now we have to remember that oxygen saturation is collected with a finger probe, and ECG is collected with a non-invasive sensor that adheres to the patient. Now, both of these can become dislodged from the patient, so both the finger probe and the sensor, which is really what causes all of those artifacts. Now, in this case, not only do we have a clear separation of artifacts and real alerts, but we have an explanation of what causes the artifacts, the sensors becoming dislodged. So the takeaway here is that interpretability and performance are not at odds for this application, and we're able to train really high-performing classifiers that give us intuition about what happens in the real life behind the scenes. So we have an explanation to go with the classification. Next, I'll talk about a project that managed a hybrid between deep learning and random forests. So as we've seen, traditionally classifiers work with tabular data, just like our previous classifier did. The random forest classifier in particular is extremely widely used because it's versatile and high-performing. Now, if the data happens to not be given to us in tabular form, people traditionally apply feature engineering and then train a classifier on the resulting table. Now, of course, we have an alternative to that, and that's deep neural networks, which everyone uses these days, and they provide a natural mechanisms to develop these new feature representations. By just combining the representation capabilities of deep neural networks and the discriminative capabilities of random forests, we obtained the first ever, I think, published hybrid model and obtained state-of-the-art on ImageNet. Now, our idea here was to make the most of whatever representations were extracted by the convolutional layers by adding an accurate classifier at the end of the pipeline. We used an ensemble of modified decision trees to obtain our end-to-end deep learning architecture. Obviously, random forests in their natural state aren't very amenable to backpropagation, so we changed them, we parameterized them, and we made it possible to perform an end-to-end backpropagation from the leaves of the tree to the nodes, and from there back to the convolutional layers. And we call these structures back-propagation trees. Let's talk about how they're parameterized. First, we have the split nodes having a soft routing of the samples with the weights determined by a parameter. We call that theta. Now, if the sigmoid function is applied to x theta to determine the weight for the left subtree, and obviously it's going to be 1 minus that for the right subtree. And this is, of course, in contrast to standard decision trees, where samples are either routed left or they're routed right. Also, we have the leaf nodes holding a distribution of classes rather than a single class. The parameters in the leaves, pi, will guide the learning procedure for a soft routing of samples. Now, for hard decisions, these will resemble empirical statistics, so they'll go to a single class per leaf node. We obtain the per sample likelihood by taking the weighted average of the class distribution over the leaves, where the weights are the leaf activations for that sample. The overall objective function will simply be the log loss over all the samples, which is, of course, differentiable. So we managed to fulfill our objective of having a differentiable objective. So now we can perform backpropagation all the way. Now, this is how the backpropagation forests were added on top of a convolutional neural network to obtain an end-to-end deep learning architecture. The network outputs just became features that were used in the backpropagation forests. The parameters of the trees and the features were updated alternatively here. We tested deep neural decision forests on ImageNet, the 2014 version, which contains millions of samples and about 1,000 classes. We modified GoogleNet by replacing softmax layers with backpropagation forests. Now, with this modification, we reduced the top 5 error from 10% to little below 8%. The best part about this is that if the images were accompanied by actual structured information, this could be naturally introduced in the model through the backpropagation forests. So we wouldn't need to fuse the features with the covariates at the end. We would actually be able to introduce them directly in the model. And I'll talk a bit more about why that's important next. So finally, I'll talk about short fuse, which is a method for learning time series representations in the presence of structured information. And this shows why it's important to consider the structured information directly in the representation learning pipeline as opposed to at the end. So for biomedical applications, we have the time series data frequently co-occurs with structured information. We have structured covariates such as patient demographics and measurements from clinical examinations. And these are common and complementary to the time series features. So it's really beneficial for the time series model to integrate and analyze them. Previous related work simply extracts the features from the time series and then separately fuses them with the rest of the structured information, which is not enough. For instance, let's consider osteoarthritis. Osteoarthritis is a condition that causes knee cartilage degeneration. Its severity is measured through the joint space narrowing. And studies indicate that physical activity has some influence on its progression, but so do a range of other factors, like the subject's gender and age. Now the question is, can we predict osteoarthritis progression given a person's level of activity and their other characteristics? So here's why it's important to use the structured information directly in the representation learning pipeline. Let's consider the case of two subjects with osteoarthritis, but different BMIs, so different body mass indices. One subject is obese and the other one is normal weight. Now, given the obese subject's higher level of systemic inflammation, cartilage response to high impact loading will be different. And thus, intense physical activity could potentially have adverse effects on the joint. In this case, peak intensity is the feature we should be looking at. Now, for the subject with a normal weight, the mean or minimum activity intensity is possibly more predictive in this case. So thus, the structured information that was present in the data set, so the weight of the subject or the BMI of the subject, had a direct impact on which features should be learned by the model and should be looked at. In this case, not considering the covariates runs the risk of producing less informative features. So to achieve this, we modified standard CNNs to account for the structured information. We're given X, the time series, with N signals and T time points, as well as S, a set of covariates. In our hybrid convolutions, the filters are parameterized with the values in the structured covariates. An element in the convolutional kernel will simply be a linear function of the covariates. Each filter uses only up to 3 covariates. The filters are then applied to randomly selected groups of the sequences, obtaining the hybrid signals Z that are the outputs of the convolutional layers. The best thing about these convolutional layers is that the output terms will contain multiplicative terms of the form WXS. So they'll contain that multiplicative XS, where X is time series information and S are the structured covariates. So what that means is S, the structured covariate, if that's a flag, that tells me whether I should look at specific parts in the time series or not at all. So that's how I can encode that maximum physical activity for subjects with a specific type of BMI, or averages for subjects with a different characteristic. So this model is considerably more flexible than other models that just fuse the representations with the time series and the covariates at the end of the pipeline. So this is a type of network that we used for our applications. And it contains 2 layers of hybrid convolutions followed by pooling layers. And that's followed by a set of fully connected layers at the end and a softmax. And we made an equivalent modification to obtain hybrid LSTMs by just adding parameters for the structured information. Let's see how well that worked. So let's go back to our prediction of osteoarthritis progression. We looked at data from the Osteoarthritis Initiative. There are nearly 2,000 subjects in this data set. We are given accelerometer data collected from these subjects over 7 days, and 650 covariates representing the symptoms, the medical history, the nutrition, physical examinations, and subject characteristics. We selected 50 based on domain knowledge. The task, again, was to predict whether the subjects are at risk for osteoarthritis progression. Here, we measured the progression by looking at joint space narrowing and testing whether it's larger than 0.5 millimeters. Again, the joint space narrowing represents the amount of cartilage degeneration that the subject experiences over a number of years. So these are the results we obtained. The state-of-the-art, results, which was obtained by engineering some features from the time series and then appending the covariates and then training a random forest model on top of it, or a well-performing classifier on top of it, only got 67% accuracy. With short fuse, we managed to increase that to 74%. And what that means is that clinicians already can start potentially making recommendations to a patient. Based on a 67% performance, you can't actually tell the subjects to move more or less because there's really not enough signal there. But with 74, you can already start thinking about making recommendations about what the subjects can do to decrease their risk of osteoarthritis. We applied this technique to also to the prediction of effectiveness in cerebral palsy treatment. So cerebral palsy is a birth-acquired condition which affects mobility. Now that's a child with cerebral palsy, and as we can see, he has trouble moving. So the gait is somewhat impaired compared to what's expected of a normally developing child. Now, the impairment is assessed in terms of what's called the gait deviation index. So joint angles are obtained during the subject's gait cycle from the motion capture using the markers. And we look at angles at the hip, knee, and ankle. And this gives us this gives us a metric called the gait deviation index. A gait deviation index of 90 or above, you're within the standard deviation of a normally developing child. If it's lower than that, if it's lower than 90, that means the gait is pathological. Now, there are a number of surgical treatments available for cerebral palsy. The problem is a lot of them are invasive. And obviously, there's no guarantee of an accurate result, which makes it difficult to plan treatment. So our task is to predict the outcomes of psoas lengthening surgery. And a positive outcome means a post-surgical gait deviation index, a GDI of above 90, or an improvement of 5 points in the pelvis and hip deviation index, which is another metric that refers to how well the hip and the pelvis muscles move. The state of the art involved a lot of engineered features by biomecanicists with appended covariates, and the outcome of that was 78%. Now, with our method, without any feature engineering, we were able to match that. So in that case, we actually performed better than late fusion with appended covariates at the end, and actually are getting above 80% accuracy right now with a fine-tuned model. I have one more thing that I need to talk about. I just have a few slides there. Do you think there's time? 2 minutes? Yeah, I can do it in 2 minutes. So we finally looked at automatically labeling a heart MRI data set. And we were looking at automatically labeling cases of bicuspid aortic valve disease. So bicuspid aortic valve is a congenital malformation occurring in 0.5 to 2% of the population. This is associated with extremely poor health outcomes. It's diagnosed following cardiovascular issues, and we would like to instead link the genetic information to this cardiac morphology. We've applied our techniques to data from the UK Biobank, and using a set of labels from Stanford experts, we've processed the MRI signals. We've obtained some telltale segments that are indicative of BAV, then used heuristics to train weak labels, which tells us roughly if the subjects have BAV or not, after which we obtained a set of probabilistic labels, which were in turn used to train a deep neural network. Finally, we obtained some labels for the entire MRI data set. We applied our labels to about 9,000 patients from the UK Biobank, and we noticed that for some of them, for the ones that we identified as having suffered from bicuspid aortic valves, the incidence of major cardiac events was much higher. So we did, in fact, manage to identify a segment of the population that was previously unlabeled with the risk of adverse cardiac events. Okay, I think that is my last result. Thank you so much.